Hello everyone, you are welcome to this channel. Today we shall be discussing numerical integration. Numerical integration is a technique to deal with difficult integral function. Application of such often lead to integrals whose analytical evaluation will be very difficult or even impossible, or whose integrand is an empirical function given by recorded numerical values. So oftentimes we have our integral function that looks like this between a and b interval function of x dx. But this function of x may be given as numerical values. As a result of that, analytical technique that we are used to may not be applicable. So as a result of that, numerical techniques have been deployed to easily resolve such function. So one of them is Simpson rule, another one is trapezoidal. Another one that we are going to be dealing with in this tutorial is the 5-point quadrature formula. 5-point quadrature formula. Briefly, this is a trapezoidal rule. Generally, integration means determining the area bounded by the curve. So, trapezoidal rule is a numerical integration method that approximates the area under a curve by dividing it into trapezoids, as shown below, and the formula is given. We also have another popular one, the Simpson rule. It's a numerical integration that contains of approximation for definite integrals over the area bounded by the curve. So, and the formula is given there. The one we are actually interested in this tutorial is the 5-point quadrature formula. It's a method for approximating the definite integral of a function using 5 specific points. 5 specific points. So we should note that. So we did the integration interval and corresponding weight. So it looks like this. When we have a function, integral function like fx dx, then we can approximate it by calculating h over 3, function at point 0, the first point, second point, third point, and fourth point. So making 5 points altogether. And h is determined by the boundary of the integral. Let's look at an example to make it clearer. So for isothermal gas phase decomposition reaction, A going to B plus C, the entry molar flow rate of A is 0.867 mole per second. Calculate the reactor volume necessary to achieve 80% conversion in a plug flow reactor. And the table of the conversion and the reaction rate are given. So we have the conversion from 0, 10%, 20% up to 85%. And we have the reaction rate given as follows. And the inverse of the reaction rate is also given. So let's look at the solution to this problem. We are asked to calculate the volume of the PFR. The volume of a plug flow reactor, or the design equation, is given as V is equal to FA naught integral 0 to X conversion 1 over minus RA dx. So you will see in this design equation that to calculate the volume necessary that we are required to do, we have to determine the range of the integral between 0 and 0.8 because we are asked to calculate it for 80% between 0 and 0.8. Then you will see that our 1 over minus RA is not a usual expression in integral because it doesn't have any relation with the x. So it is given as numerical values in this table. 1 over minus RA is given as numerical value. So therefore we have to use numerical integration for this technique. So let's see how it works. We have already seen that our x will be 0.8. Then the 5-point quadrature, we need to determine our h. Remember this, fx dx. What is our fx here? That is 1 over minus RA. Our dx is here. So we need to determine h. How do we determine h? H is equal to x4 minus x naught over 4. What is x4? The last point here, upper band, which is 0.8. Minus x naught, which is what? 0 divided by 4. So that is 0.2. That means our h is 0.2. That means to have the 5 points, we need 0, 0.2, 0.4, 0.6, as well as 0.8. So that is 5-point quadrature that we are asked to determine. So we need to determine all those functions at those points in the x direction. So let's see. the formula remains V is equal to FA naught and the integral. So, and we have been told that we have to be what? FA naught H over 3. H is what? 0.2. So that means FA naught is already known, 0.867 multiplied by H over 3. You remember the formula? The formula is H over 3 for fx dx. So H over 3, which is 0.2 divided by 3. And then 1 over minus RA at the first point, which is 0.0, is what? At 0.0 is 189. So that means, and the formula says what? The formula says F naught. So that means we have to write 189 here. Plus, the formula says for F1, our F1 is at the second point, 0.2. So x at 0.2 is what? 182. That is 1 over minus RA at 0.2 is 200. Sorry, it's 0.2 is 200. So that means, and the formula says what? 4 times that. So that means 4 times 200. 4 times 200. So 4 times 200 plus the third item we need is what? 2F2. F2 is at 0.4. F2 is at, so 1 over minus RA at 0.4 multiplied by 2. So we go here, at 0.4 is 250 multiplied by 2 as given by the formula. So we say plus 2 times 250. Then the fourth point is what? Our fourth point is at 0.6, and that is 4F3 at 0.6. So at 0.6, we are given 400 for 1 over minus RA, and we have to multiply it by what? By the 4. 4 times what? 4 times 400. 4 times 400. So plus 4 times 400. So finally, plus at 0.8, the last point, the fifth point is 0.8. So, and that is 800. 800 there. So, with that, we are having the calculation shown below. So, if we evaluate that, we are going to get 225 DMQ. So, which is the evaluation using the 5-point quadrature formula. So, ladies and gentlemen, that is how to apply numerical integration to integral, having the function of numerical values. So I hope you enjoyed the tutorial. If so, please click my subscribe button, and if you have any comment, please send it to me from the space below. Thank you.